Function of a GFCI. Everybody know how a GFCI works, right? Okay, basically, you sense current going in. It goes to the load, whatever it is, and then the current comes out through that same sensor. And all it does is compare current going to the load, current coming from the load. If current is off, if what returns is less than what goes to the load, then through solid state stuff, it trips the supply to that, the breaker or whatever trips in the GFCI, okay? It depends on what kind you have. That current is called leakage current. It's not the same as a short circuit. A short circuit is huge amounts of current, right? GFCI protects against leakage current. That's a small amount that's leaking through some low resistance connection somewhere, okay? Whether you might have a crack in some, you know, in a motor, all your wires are insulated, right? They're dipped, laminated. You might have a crack there, okay? Or you might have a wire that's through vibration rubbed through its insulation or something like that. So a GFCI trips on leakage, and there's actually two types. One's for personnel. That trips at a real small value. We talked about this in electrical safety, 4 to 6 milliamps, right? Okay, 4 to 6 milliamps, if there's a difference in that amount, it trips in about, I think it's a 40th of a second, something like that. So really quick, and that's for personal protection. The other one is for component protection. It trips at about 20 amps. It's just like a GFCI. It's just like a circuit breaker, but it's ground fault. Okay, so that's kind of a, here is a little bit less than what I just talked about. So. And then 5, warning signs or clues an electrical hazard exists. If you got a GFCI that trips, and you reset it and it trips, and you reset it and it trips, there's probably a reason why it trips, okay? Circuit breakers. If you're blowing fuses and you replace fuses and you blow fuses, there's a reason, okay? Circuit breakers. If you got to go keep resetting it and your boss tells you to tape the thing shut, there's a reason that thing trips, okay? If you're using tools or an extension cord, okay, and they're warm, then that means you've got excess current going through that thing. Remember I²R losses, right? Current, you got current flowing through something, you're going to have heat losses. That's heat, okay? So I² is the big factor, I²R. So the more current you have, the more heat's generated. If the thing is warm, it might be your drill from using it, and there might be a reason for it to be warm. It might have been used for 30 minutes straight, and it's not designed for that. But still, there's if it's too warm, if it's warm at all, there's a reason why it's warm. So you need to investigate. Okay, worn or flayed insulation around a wire connection. That's just really common sense. Okay, if coming out like this, okay, Jeremy likes to use this as an example. All right, that guy right there. All right, I can see the internal wires. The outside cord or the outside plastic is not connected. Okay, now that doesn't cause any problem. There's no integrity loss there. This thing works fine, but there's a reason that thing's broke like that, and that's because I wrap it too tight. Okay, so you need to investigate and correct it. It's fine, but it should have some more support there. So your drills and your hand saws and stuff are or your electric saws are the same way. Everybody's seen that thing pull out. Okay, you've all made connections where you wire something and you crimp a terminal on there and you see about 1/8 of an inch of bare wire. Well, that 1/8 of an inch of bare wire shouldn't be there. Those terminals have that outer case that you crimp on there so you don't hit that wire. That's if a paper clip or a metal shaving falls in there and just happens to fall there, yeah, it's a big bucket, small area, but if it does, I mean, it's not likely to happen, but it could happen. So wire is a big thing when you're, and you guys will all see that when you get into industry. You'll see in these boxes you're looking at, you'll see poor wiring and good wiring. So, okay, introduction. An average of 1 worker a day. An average of 1 worker is electrocuted on the job every day. What's electrocution mean? Death. So somebody dies every work day. Somebody dies. Okay. We covered this is objective 1. Electrical shock, burns, and falls. Terminology. You guys should know these. Current, resistance, voltage. These are basic. These aren't your level of terminology. Conductors, insulators, and grounding. Okay. Grounding in here, it says a conductive connection to earth which acts as a protective measure. Okay? All it does is, if you're properly grounded, you're not the alternate path for current flow. There's something else there that is. That's what grounding is. Okay? It keeps you from being the path from potential to the earth. Okay? That's what grounding does. Electrical shock. If you get a shock, that's when current passes through the body. So if current passes through your body, you've received an electrical shock. Okay? Severity. Now we talk about one other one, but path to current flow through the body, the amount of current flow through the body, the length of time, and what was the other one we talked about? Condition, very good, condition of the body. Whether you're wet or dry, whether you're exhausted, if you're hydrated, all that kind of stuff. Okay. Path, if it goes in here and out here, it's not good for this part of the body, but it doesn't affect your heart really. Okay. So the worst case is from this hand to this hand through the chest. That's the worst because there's the least resistance and all that kind of stuff. The amount of current, what do we say? How much current does it take to kill you? 1 milliamp, right? Does anybody think it's different? 1 milliamp, that's the number we use. That can kill you. Is that right? 100 milliamps, is that what you said? No, it's actually.
I thought it was fine. Yeah. You're the teacher. Yeah, the interpreter.
Okay, 100 milliamps is what we advertise to kill you. Okay, that's what we advertise, 100 milliamps. Okay, that's what it takes for your heart to stop. Now, there's other things that can cause. It's like heart palpitations and then fibrillation and that kind of stuff. So there's different levels. I think in here it says 75. Somewhere in here it'll say 75 milliamps. So we advertise 100. Somebody said 1. So and it's going to be different wherever you go. You're going to see some places that say 50, some places that say 150. Just know that it doesn't take much current. Okay, it doesn't take much at all. Okay. Length of time, that's kind of a given. The longer on there, the more damage is done, right? If you put a hot dog on the grill for about 8 seconds, it's still kind of raw. But if you put it on there for 8 minutes, it's crispy. So time is a big deal also. Low voltage does not mean low hazard. Remember, just a little bitty shock still can kill you because you fall off your ladder. Okay, dangers, here it says 75. Currents greater than 75 can cause ventricular fibrillation. Will cause death in a few minutes. Not much current. A small power drill uses 30 times as much. So a little bitty drill uses 30 times what it takes to make your heart start beating funny. Okay? So that's not much at all. Electrical shock, you guys should all know, I mean, I know you guys know this. So just when you have a difference in potential and you give a path for current flow, current's going to flow, right? So the greater that difference in potential, we advertise 50 volts here. I think OSHA does too, somewhere. 50 volts is considered high voltage. That's what it'll take to hurt you. So if you figure 100 milliamps is what it takes to kill you, to make your heart stop. I'm not saying kill you. Make your heart stop. Then that means your minimum body resistance through your chest area is probably about 500, and that's when that's when you have a cut in this skin and a cut in this skin, because skin is resistance. Okay, so if you have an open wound in both hands and through your internals only, when you're exhausted and all this kind of stuff, they say about 500 ohms. So that comes out to your 100 milliamps. Okay. All right. Difference in potential. Current will flow if they're connected. You guys, I'm sure you know this. I'm just going to read it because it's here. Household wiring, that's where most accidents, 110 is what kills most people, okay? Most reported electrical shocks are in the household, okay? Black wires are 110 volts relative to ground. White wires at 0 because they're connected to ground. Okay, that's where a lot of the people that run wire themselves, they get that backwards, okay? Black is hot, white is neutral in your 110. Is there a problem if you mix it up? Alternating current flows both ways, right? Is there a problem if you mix it up?
You're switching the ground, aren't you?
Aren't you still having voltage flow? I mean current flow, I mean? You're still having current flow, right?
So there's no problem.
There's danger
But
to
your white
somebody
one's
else
hot.
that comes up. and
Your
tries
white
to-
one's hot, but the equipment will still work.
Right, but your white one's hot, so if somebody else comes up, grabs onto it thinking it's neutral, it's hot.
Right. Most switches, when you turn a switch off, most switches only break one conductor, okay? And they break the hot conductor. If you turn something off, you break that connection through, say it's a light and you've got it wired up so white's to hot, black's to ground. It'll still turn that light on. And when you turn that light switch off, that light will still turn off because there's no path for current flow. But if you turn that switch off and then you stick your finger in that socket and you're touching the ground, now you've got the hot going through your finger to ground. So the light switch doesn't give you any protection, okay? If you have it plugged in and the light's turned off and you spill water on it, right? Okay, if it's wired up correctly, there's no way that current can flow through that pile of water. If it's wired up incorrectly, that pile of water is now can conduct. So it is a big deal to make sure it's connected correctly. Black is hot, white is neutral, or it's connected to ground. Okay, if you come into contact with energized live black wire and you also combine a white grounded wire, current will pass through your body and you will receive a shock. So that's if you grab hot lead and a neutral lead. Okay, you're gonna need a shock. Duh. This is a little bit more. If you contact both wires at 240, you will receive a shock and possibly be electrocuted. Duh. Okay. Electrical burns, most common shock related, that's electric shock, not where you turn white and lose all your freckles and all that kind of stuff. The most common electric shock related non-fatal injuries of burn. I mean, you look at that, that's pretty minor. You got a hole there, you could have gone in there. Who knows? Occurs when you touch electrical wiring or equipment that is improperly used and maintained, typically on the hands, because that's what you do with your touching. Very serious, because really it cooks. It cooks that meat. You know. You can take a wire, and I was going to do this for the demonstration, but I didn't have any more hot dogs. Take a wire, get electrical safe, and plug. I probably shouldn't tell you this because some of you will do it. Take the black and the white connection, plug it in, and then turn it on, and you've got current passing through there. And it will cook that hot dog from the inside out. It doesn't take long. It doesn't take long, and you have a nice, warm, toasty hot dog that's cooked on the inside. It's probably pretty good. I'm getting hungry. Actually, make sure you use electrical safety stuff, but if you use a dill pickle, it's got all that salts and stuff in there, and it'll light up and flash and stuff.
Really?
Use electrical safety stuff when you're electrifying food.
The reason I know this is because this was the demonstration that I received when I got certified to teach OSHA. That's what the OSHA instructor used to show you what happens when electricity flows through meat. Okay, it cooks it, and your arm is meat. I mean, that's just like a roast off of a cow or something. If you cook it, once it's cooked, it's dead. It's a dead cell. It's no longer. You can't cure that. The only way to cure that is to scrape it out. Okay, just get rid of it. So then you've got this arm. If any nerves are cooked, you have no nerves. I mean, you're done. So whatever cooks is gone for good. Okay, so it is a big deal. These burns are a big deal. If you cook and kill those cells, they're gone for good, and you can't replace them. All right, so it is a big deal. These, the burns they talk about, and again, time, the amount, the path, that all goes into how serious it is. Falls, that's pretty obvious. The guy gets zapped there, goes, oh crap, and then he falls back off the ladder. So falls are a big deal. Indirect or secondary injuries, they call them. Inadequate wiring, we talked about this. This is also one of the learning objectives. Hazard exists when a conductor is too small to safely carry the current. Okay, so just make sure that when you're wiring something up, you go to your uglies or you go to your NEC and you figure out what the maximum current could be going through that system and gauge your wires accordingly. Okay. Here's the example. If you use a portable tool with an extension cord that has a wire too small for the tool. Most people think extension cords, you go buy them, but some of them are pretty thin. Some of them are big honking things, okay? That has to do with the size of wire that's in there. If you've got a drill that you're, you know, a big heavy drill that you have 12 gauge wire going to the drill itself, then you ought to have 12 gauge wire in that extension cord. If you've got 16 or 18 gauge wire is what's used for Christmas lights, okay? If you've got something like that and you're pulling a lot of current through there, then you're going to have heat, you're going to have insulation breakdown, then you're going to have insulation failure and shock and all that kind of stuff. So that's inadequate wiring. Tool draws more current than the cord can handle, overheating, possible fire without tripping the circuit breaker. Circuit breaker could be the right size for the circuit, but not for the smaller wire extension cord. Okay? I don't know why that's there. Grounding says some of the most frequent violated OSHA standards. Grounding is a huge violation. I think it is the single most OSHA violation for electric. Okay, metal parts of a wiring, touch switch plates, ceiling light fixtures, conduits should be at 0 volts relative to ground. Housing of motors, they can become energized if they're not grounded properly. If you come into contact with an improperly grounded electrical device, you will be shocked. Okay? If it's not grounded, that means if there's a fault, the current has nowhere to go. Current's supposed to have a path to ground if there's a fault to anything. And if it doesn't, and you touch it, now you're the path to ground. So you don't want to be there. Okay?
Weren't you used to able to ground to cans like in lighting and the ceilings?
Do what now?
Back in the day, you used to be able to ground to the can.